my pleasure again to come to you and see how science does confirm biblical creation. One of the privileges I have as a scientist, I get to see aspects of God's creation that a lot of people don't get to experience, and it's just my joy to share that with others, and so that they can see God's majesty revealed in what He's created. There was a movie a few years ago, National Treasure, where Nicolas Cage finds a secret code on the back of the Declaration of Independence, and it leads him to other clues and so on. And obviously, the code was put there by very intelligent people, and that implies intelligence when you find a code like that. What if there were a code embedded in numbers like 1, 2, 3, 4? What if there was a secret code embedded in them that we finally got around to discovering? What would that imply? What if there was a message inside numbers? What would that imply? It would tell us something about the intelligence of the person who made numbers. Now, we don't often think about God creating numbers because they're abstract. We think about God creating animals and stars and planets and so on. But numbers, God is responsible for them as well. Even though they're abstract and conceptual, God's sovereign over the abstract just as much as He is the physical universe. And as a matter of fact, there is a secret code built into numbers that was discovered in the 1980s. It's been there since creation, but it wasn't until the 1980s we got smart enough to finally decipher it. And it is mind-blowing. And this is something that I read about when I was pretty young, really, and it was mind-blowing to me. And I want to share this with you because I dare say there is no secular or atheistic explanation for what I'm going to share with you today. This secret code only makes sense in the Christian worldview. And so we're going to have to talk a little bit about that and what that means. When I was young, very young, and my mother would prepare these wonderful meals, but sometimes she would put broccoli on the plate, which I didn't really care for. And in rare moments of maturity, I would eat the broccoli first, get it out of the way, because the rule was you had to eat everything on your plate. So I'd get the broccoli out of the way first so that I could then enjoy the rest of the meal. You know what I'm talking about? Yeah. So in that spirit, we got some broccoli to do first. But stay with me because it's going to get really good, okay? You won't be able to enjoy the rest of the meal unless you go through the broccoli. So we're going to talk first about sets. Now, a set in mathematics is just what you think it is. It's a group of, in this case, numbers that have a common defined property. And so you can have different types of sets out there. And in most sets, some numbers are included in the set and other numbers are excluded from the set. This is pretty easy, and it depends on how you define the set. So you could have the set of even numbers, those numbers that are evenly divisible by 2. And in that set, those numbers would be included in it, and those other numbers would be excluded from it. That's pretty easy. That's the set of even numbers. We could consider the set of negative numbers. Now, that's a different set, isn't it? And so a different set of numbers will be included in there, and then those other ones will be excluded. Now, for those two sets, you can tell just by looking at the number whether or not it belongs, right? In this case, if it doesn't have a little negative sign in front of it, it doesn't belong. And if it does belong. So that's pretty easy. You can tell just by looking at the number. But there are some sets that have a more complicated definition, and you can't tell just by looking at the number whether or not it belongs. And so we're going to talk about a particular set that's called the Mendelbrot Set. This was discovered in the late 1970s, early 1980s, named after the person who really discovered this, Benoit Mendelbrot. He was a math guy and a computer guy. He worked at IBM. This set is defined according to this little formula that you see right here, where it's the set of all numbers, C. C is a number that is potentially part of the Mendelbrot set. We're testing it, for which this other number, Z, remains small according to this little formula. And it looks very complicated, but it's really not. I'll take you through it. The little n just means that that's a particular value of Z. N plus 1 is the next value of Z. So there's lots of values of Z. There's a sequence. And if that sequence of Z stays small, like if it's all zeros, that would be small, then the other number, C, is part of the Mendelbrot set. On the other hand, if the sequence of Z gets very big, if it goes 1 to 100, a million, a billion, then C is not part of the Mendelbrot set? And we'll do a couple of examples to let this sink in. It's pretty straightforward, really. So we're going to ask, is the number 1 part of the Mendelbrot set? So C equals 1, okay? And we're going to plug that into our formula then. So we have z squared plus 1, because that's the number we're testing. That becomes the new value of z. Now, the first value of z is 0 by definition. So that's the first value. So we plug that in, and we have 0 squared, which is 0, plus 1 is 1. Yeah, 0 squared plus 1 is 1, right? Even the Common Core folks got that one, right? Okay. So that's the next value of z, okay? And what we'll do is we'll put that 1 back into the formula. That's the new value of z. So now we have 1 squared, which is 1, plus 1 is 2, okay? You plug that back in, so we have 2 squared is 4. 2 times 2 is 4, plus 1 is 5. Okay, you're getting this. You put it back in, 5 squared, 25, plus 1 is 26. Okay, we put that back in. 26 squared is a big number, and you put that back in. Okay, now you see what's happening here? Is the sequence of z staying small? No. So is the number 1 part of the Mendelbrot set? No, because it has to stay small for it to belong. You see? So we'll do one more example just to make it clear. Is the number -1 part of the Mendelbrot set? So this time c equals -1, and we'll plug that in. So it's going to be z squared minus 1 is the new value of z. Z always starts as 0. So we have 0 squared, which is 0, minus 1 is -1. We put that back in. -1 squared is +1, right? Because a negative times a negative is a positive. Minus 1 is 0. We put that back in. 0 squared. Wait, this looks familiar. 0 squared minus 1 is -1. Put that back. Oh, wait a minute. See what's happening there? 0, -1, 0, -1, 0, -1. Interesting. And you can see it'll do that forever. Is z staying small? Yeah. So is the number -1 part of the Mendelbrot set? Yes. Okay, you got it? Pretty easy, really. It's tedious, but it's easy, right? And you could check any number that way. All you could do is run it through that formula, and the sequence of z will either stay small, in which case the number is part of the Mendelbrot set, or the sequence of z will get big, in which case it's not part of the Mendelbrot set. And you could run that through, and it's easy as pie. It's just kind of tedious. There's one more complication, and then we get to the really cool stuff. The other complication is that the Mendelbrot set also includes what are called complex and imaginary numbers. Okay, so an imaginary number is a number that when you square it, you get a negative number. And that's a little hard for us to understand, and so they call them imaginary. It's just a name. I hate that they have that name because it makes it sound like they don't exist. You know, they're fabricated. No, they do exist. Imaginary numbers do exist. And to add insult to injury, the numbers that are not imaginary they call real. But that's just terminology. Both are equally true, let's put it that way. But how do we have a number that times itself is negative, and it's represented by a lowercase I? That's the kind of the primary imaginary number when I times I is -1. How do we make sense of that? After all, imaginary numbers are not positive because a positive number squared is positive. And yet, the imaginary number times itself is negative. Imaginary numbers are not negative because a negative number squared is also positive. And imaginary numbers are not 0 because 0 squared is 0. Weird. So we have a number that's not positive, it's not negative, and it's not 0. And that leaves us kind of scratching our heads a little bit. We have trouble with that. Well, I got news for you. Not everything in this universe is intuitive. If you've ever had a class in quantum mechanics, you know the universe doesn't work always the way that we expect it to. You know, our intuition really is based on experience. And the fact is most adults don't have experience with imaginary numbers, and so they seem strange. But it's just a matter of experience. When you were a little kid, negative numbers probably didn't make a lot of sense, right? You know, I can have 1 apple, I can have 2 apples. How can I have -2 apples? That doesn't make sense. How can you have less than nothing? You get a little bit older, you get a bank account, suddenly negative numbers make a lot of sense, right? Yes, I can have less than nothing. Well, imaginary numbers are the same way. You gain a little experience and you find, yes, there are numbers that when you square them, you get a negative, but they're not positive, they're not negative, and they're not 0. How do we make sense of that? One way to do it is if you consider a number line. So here we have a number line, Now, the positive numbers are to the right of 0 along that number line. The negative numbers are to the left of 0 along that number line. So how do we represent a number that's not positive, not negative, and not 0? Well, you put it up above the number line like that. It's not on the number line. It's on a different axis. And by multiplying I by the other real numbers, you can have all kinds of imaginary numbers. And you can think of them as being on a different axis. So the real numbers are along this axis. The imaginary numbers are along that axis. And that makes sense. You can see that the imaginary number, it's not positive because it's not to the right of 0. It's not negative because it's not to the left of 0. And yet it's not 0. That kind of makes sense. And then you can also have numbers that are called complex, and they're off axis. They're called complex because they have a real part and an imaginary part. But it's one number with two parts. And usually the real part is represented by the x-axis, and then the imaginary part is represented by the y-axis. And so you can plot any number in a plane by those two components, the real component being the x and the imaginary component being the y. That's kind of neat. I can represent any number on a plane. Very convenient. So the Mendelbrot set also includes these imaginary and complex numbers. And the only thing you need to remember, they obey all the ordinary rules of algebra. It's just that when you multiply I by itself, you get -1. That's the only thing you have to remember. Everything else, it's just ordinary algebra. So what we can do then is we can make a map, because I'm trying to figure out if there's a pattern to the numbers that belong to the Mendelbrot set. And it turns out there is. But it's not obvious, right? Because you can't tell just by looking at a number whether it's going to belong or not. You have to run it through that formula, and that's kind of tedious. But in the 1980s, computers were starting to get fast enough where they could iterate that formula a number of times, and they could analyze to see whether z is getting big or staying small. And so what we can do is we can have the computer check all these different points, and we'll see if there's a pattern to the Mendelbrot set. And so we'll take the points that belong to the Mendelbrot set, and we'll color those black. That's arbitrary. That's the way Benoit Mendelbrot did it, and we follow his example. So, and you have the computer check more points, and you find that all those points right there belong to the Mendelbrot set. When you run it through that formula, z stays small. And then the points that do not belong, we'll color those red, or some other color. It doesn't really matter. And so we already checked the point 1. We found that the number 1 does not belong to the Mendelbrot set, so it gets colored red. And had we checked these other points, we would find that they do not belong. And so you see, as you plot more and more of these points, a pattern starts to emerge. What's it going to look like? Well, you have the computer run through thousands and thousands of points. You have the computer check each one of those numbers, and a pattern emerges, and the pattern looks like this. It's really interesting and unexpected. Nobody was expecting that when you made a map of the Mendelbrot set, it would look like that. Remarkable. And so let me remind you again what you have here. It's a plot of the points that do or do not belong to the Mendelbrot set. The points that are colored black do belong. The points that are colored red do not. And I even shaded it, so points that are almost on the Mendelbrot set but not quite are bright yellow. And so it's kind of shaded. So if the sequence of z goes to infinity really quick, it's dark red, and if it goes to infinity slowly, it's kind of a bright yellow. So it kind of, you don't have to do it that way, but it increases the contrast, makes it easier to see. So now we don't have to run it through that formula because the computer's already done the hard work for us. We can look and we can see that the number -1, you can see it's part of the Mendelbrot set. You can see that the number 0 is. Had we run it through the formula, z would stay bound, and so on. The half I is part of the Mendelbrot set. So I'm going to remove the axes now, because it turns out this shape is remarkably interesting and unexpected, and it'll turn out to have a lot of beauty in it as well. The shape itself is, this is a mathematical plot. I guess we'd expect it would have some mathematical properties to it, but everyone was surprised by the properties it has. The main shape that looks kind of like a heart, that's called a cardioid. And a cardioid is what happens when you take a circle and you take your pencil on it and roll it around another circle of equal size. The shape you'll get is a cardioid. And you can see that, sure enough, the main part of the Mendelbrot set is a perfect cardioid. All the other shapes that are growing off of it are circles. All these perfect circles attached to the perimeter of the Mendelbrot set. And then you see some other features, like these little tendrils that grow off of it, and a spike over on the left, kind of that juts out. That's kind of interesting. What's that all about? Well, The interesting thing is we can zoom in on this because we can have the computer plot it at higher resolution, and we find that this shape has some really interesting mathematical properties to it. You notice that that top circle there, it's got a circle on top of it, another one on top of it on smaller and smaller scales, and it goes out and forms this little tree, and it's got 3 stems to it, including the trunk. So it's got a trunk and 2 stems for a total of 3 branches. You see that there? Now the next one to the left branches into 5. Can you see that? I mean, it's kind of small, but you can see the 5 branches there. The next one is 7, 9, 11, 13, 15. It's all the odd numbers. And by the way, they don't stop. They go to infinity. There's an infinite number of them. They get smaller and smaller, though, and so you have to zoom in more. But so somehow the Mendelbrot set knows how to count. It's kind of remarkable. And then on the other side, you have the odds and the evens. You have all the numbers there in terms of the number of branches. Now, it's remarkable enough that they have branches at all, because who would have thought that when you run numbers through that little formula, you get that shape? It's remarkable. Nobody was expecting that. And it's even more remarkable that it has the ability, apparently, to count in terms of the number of tendrils that grow off of each bud there. And, of course, you can take 2 of those numbers, like 5 and 3. Now, 5 plus 3 is 8, okay? And it turns out that the bud in between those 2 has 8 tendrils. Interesting. And that's true of all of them, both on the left side and the right. The bud in between the 2 adds the number of tendrils on each one. So not only does the Mendelbrot set know how to count, it knows how to add. Interesting and strange and remarkable. Well, let's go back out take a look at the overall shape here. So again, you have that cardioid, that's the heart-shaped structure, circles growing off of it. And then on the left side over there, you got this kind of spike that goes out. And you see there's this little bump on the end of the spike. So let's take a look and see what that looks like. So we'll zoom in on it. And that little bump, turns out, it looks like the entire Mendelbrot set. It's a mini Mendelbrot set. And it's almost identical to the parent, except it's got extra spikes growing off of it. But the basic shape's the same. It's got the cardioid and the circles. And, it has a little spike growing off of it, too, with a little bump. What could that be? Well, let's zoom in on that. And, interesting. Absolutely fat. And it's got extra spikes growing off of it. And that's got a little bud. How about that? Now, of course, you could do that literally forever. And there's an infinite number of baby versions built into the Mendelbrot set on smaller and smaller scales. Fascinating. Absolutely fascinating. And take a look at how small this is compared to the original when we zoom back out here. Look at how tiny it is. Isn't that remarkable? And the fact that it repeats infinitely, and it doesn't lose complexity, it actually gains it each time you get more extra spikes growing off of it. Very remarkable. Well, to anticipate my conclusion in this, I'm going to suggest to you that this shape tells us something about the way God thinks. God's understanding is infinite. Numbers are an aspect of God's mind. God is responsible for numbers. And so it makes sense in the Christian worldview that when we explore and study numbers, we find intelligence in them. We find evidence of patterns. And not only intelligence, but infinite intelligence, because this thing repeats infinitely. A structure that repeats itself on smaller and smaller scales is called a fractal. So the Mendelbrot set is one example of a fractal. There are other types of fractals. There are other sections of the Mendelbrot set that are fractal. We could zoom in, for example, on one of these little tendril features here and zoom in on that. And you'd say, well, that's interesting. You think what's going to stop at some point, right? Eventually it'll even out and but it just keeps going. It's infinitely wiggly, you see. It's wiggling around like that, and you zoom in on it, and it keeps going and keeps going and keeps going. It's just mesmerizing and watch this thing and see the scale here. And it gives you a little taste of what God's mind is like, to be able to think infinitely. We can only process just a little bit of information at a time, but God's mind is truly infinite. So one of the interesting areas to explore, and what I want to do now is just kind of spend some time exploring this shape that exists in the mind of God and has existed in the mind of God from creation, that was only discovered in the 1980s. And we can zoom in, for example, on this cusp between the main cardioid and the disc. And we find they call it the Valley of the Seahorses, because you see over on the right side, it looks like seahorses. They're upside down, because the way we've zoomed in on them here. Now, the colors are arbitrary. I can make them whatever I want, and we'll change them every now and then just to keep things interesting. But just keep in mind, black always represents numbers that do belong to the Mendelbrot set, and then colors represent those that do not belong to the Mendelbrot set. And bright colors are very close to being on the Mendelbrot set, but not quite a part of it. So let's zoom in on one of these seahorse structures over here. You see it looks like an upside-down seahorse. Isn't that fascinating? And quite beautiful. And I need to explain a little bit about what this means, because if the points are very bright, that means it's very close to the Mendelbrot set. And you might look and say, but yeah, that bright hub doesn't look like it's anywhere close to it. It is. It's just, you need to realize that there is a very thin black thread that's wiggling around and making that shape, you see. It's just so thin, it's thinner than the pixels that the computer can plot. So everywhere you see structure like that, there is a very thin black thread that's winding around and creating that wonderful shape. So really quite remarkable. And who would have expected that little formula, z squared plus c, when you run numbers through it and you find out which ones belong, you get that. I think it's amazing. Well, let's zoom in and find out what this seahorse is made of. It's the central hub there looks kind of like a spider web type structure, right? You got the spokes and the rims around there. And I've found from experience, you can zoom in on the center of that till your heart's content, and it doesn't really change very much. It goes on infinitely. So again, the infiniteness of the mind of God. And so I thought, well, okay, let's go off to the side and figure out what these strands of the spider web are made of. So let's go off to the side here, and we find that the strands are made of more spider webs, which is kind of interesting. And we zoom in a little bit more, and you find that there's sort of two hubs there. You see the bright yellow hubs. And then in the middle, it goes from 2 to 4. And as we zoom in, it'll go from 4 to 8 to 16, 32, 64. It doubles each time. And as we zoom in on that central hub, we find, oh, isn't that interesting? You see it going from 4 to 8 to 16 and so on, and in the middle, of course, you have another baby Mendelbrot set. Quite fascinating, really. And again, there's an infinite number of these babies built into the overall shape, which I think is amazing. And again, look at how small this is compared to the overall shape as we zoom back out. It's just a tiny little infinitesimal, and we could have zoomed in on any one of those strands. I just picked one at random, and there it is. So pretty remarkable.